Okay, continuing on with solutions, we need to be thinking about the next part of this is expressing concentration in many different ways, and I want to point out to you that we have some of the old familiar ones, molarity, but then we have some that sound like it, and actually I'm going to go ahead and remind you that molarity is a capital M, but molality is another concentration term, and that's a lowercase m. So if you write a lowercase m, I'm going to think you mean molality. So if you mean molarity, uppercase, if you mean molality, lowercase, we'll have mole fraction and weight percent, and then parts per million. Okay, so I'm going to kind of walk you through each one. Definitions first, and really to be successful at this, you need to know the definitions. And there are some picky details in these definitions that you should be aware of. So to begin with, molarity, you're pretty well aware of that. Moles of solute, but here's where maybe we're going to make a distinction that has not been made before. Moles of solute per liters of total solution. You see there's total solution. So that's just not liters of solvent anymore, not liters of water, for instance. That's the total final volume after solute has been added to the solvent. So that's liters of solution, okay? That's important. You better remember that because down the road, well, you'll see shortly why that's important, but you got to kind of keep it straight. Then we have moles of solute divided by kilograms of solvent. That's molality. So in this case, you divide the moles of solute that you're dissolving by the kilograms of solvent that is being used. Notice it's not a volume term here. So you got to know kilograms of solvent and then moles of solute. Then we have mole fraction. Now, mole fraction can be, sometimes you'll see it abbreviated like so, okay, with that Greek letter chi, I think it is, but that's, it looks like a funny looking X. Well, that's mole fraction. In mole fraction can be, you can have the moles of one of the components that you care about divided by the total moles. So this is a fraction, and it's unitless, okay? And we'll talk about that in a little bit. Weight percent or mass percent is probably a better way of saying it, although in old language you'll still hear weight percent, and sometimes I'll even call it that, but usually mass percent's better because we're dealing with grams. So you take the grams of one of the components that you care about and divide it by the total mass of all of the components that are present in the solution. Multiply that by 100%. And so that gets reported in a percent. And then parts per million, you'll often see this used, where I see this most often used is by analytical chemists. And so like the EPA, it might tell you analytically how many parts per million can you have, say, mercury in your water in order for it to be safe. You know, questions like that. So parts per million is another way of representing, and it's parts by mass. So it's a way to represent a concentration. So what you do is you say a sample, if you have 1 gram of a substance in a sample with a total of mass of 1 million grams. So it's 1 gram in a million grams. One example of this is there's 1 million milligrams in a liter of water. Just 1 gram per milliliter, so you can do your math from there. So there's 1 million milligrams per liter of water. So if you had 1 milligram of your solute, whatever's dissolved in the water, then 1 milligram per liter of water would give you 1 ppm, or 1 part per million. Okay, I'm going to do some math on this and we'll calculate some things here. So the first one is molarity. Get your moles, divide your, so we're going to take 5 grams of sodium hydroxide, dissolve that in 2 kilograms of water. And by the way, 2 kilograms of water is 110.98 moles of water. We'll say it has a final volume of 2.01 liters, and that's, to be clear, liters of solution. Okay? And then you can divide by the molar mass, and get your moles. So we have, 5 grams of sodium hydroxide is 0.124, and these are non-significant. So 0.124, almost 0.125 moles of sodium hydroxide. 110.98 moles of water is 2 kilograms. So let's apply this. So for molarity, this should be old hat for you by now. You take 0.1, 0.125, I'm going to just call it 0.125 moles of sodium hydroxide, so that's your solute. And then we need liters of total solution. Here's liters of total solution divided by 2.01 liters. And that gets you 2.0622 molar, or moles per liter. So that you could use either one of these as your units. So that's what I got. See if you got that. That makes sense. So now let's move on. Molality. Moles of solute divided by kilograms of solvent. So in this case, we have our moles of solute, and molality is a small m. And so we'll take, again, we'll just go with 0.125 moles of sodium hydroxide. In this case, we have 2.00 kilograms of H2O. And if we plug that in, we get 0.0625 molal. Or you could say moles per kilogram of water. So we'd say that's molal. So that you can see that when you have a pretty dilute solution like we would have here, that molality can resemble molarity. They're pretty close, but they're not the same. But when the solution is a lot more concentrated, you're never going to be able to see that that kind of relationship. They won't be that close. But for really dilute solutions, you can interchange the two, it turns out, but not going to be the case if they're more concentrated. Okay, so then we have mole fraction. So mole fraction, in this case, we're given, we'll do 2 mole fractions. One, we'll do mole fraction of sodium hydroxide. So we'll say, in this case, let's let sodium hydroxide be component A. Okay, so if we do that, we know we have 0.125 moles of sodium hydroxide, and then divide that by 0.125 moles of sodium hydroxide plus about 111 moles of water. I just rounded the 110.98 to 111. So really, let's call water then component B. So I'll just call that component B, and that's component A. So I have to sum the two together to get the final total amount of all components, okay? And so let's do that calculation. And we'll write it like this. I'll write it as the mole fraction of sodium hydroxide. And punch that into the good old calculator, and you get 0.00112. And there's no units on that. So that's the mole fraction of sodium hydroxide. Now, if I want to calculate the mole fraction of water, I just do the same calculation, but instead replace 0.125 with 111. That's one way to do it, but there's another way. Whoops, hit the wrong button here. So the mole fraction of sodium hydroxide, in this case, plus the mole fraction of water, since those are the only two components that are present, are equal to 1. So I could just take 1 and subtract from it my mole fraction of sodium hydroxide, and I can get my mole fraction of water. So 1 minus, and it's exactly 1, so it has an infinite number of significant digits, right? And so we can write this out. And so this is the total of both mole fractions, and this is the mole fraction of sodium hydroxide. And so I plug those in, and if I want the mole fraction of water, I can do the math, and I get 0.998, and I can go out to the 5th decimal point. So 888. Those are all 8s. So that's my mole fraction of water. And just to double check, you can go ahead and plug that in place of that, and you should get the same number. And by the way, I just did it, and it totally gives me that number. So the last one I want us to look at then, I'm going to erase this now. Well, maybe I won't, because it won't let me. Yep, there we go. I'll erase this out of the way, just to clear some room. All right, that's 100%. Now I'm going to go ahead and calculate my weight percent of sodium hydroxide in this case. And so I'll take that. I'll take my 5 grams divided by 2,000 grams of water. This is sodium hydroxide. That's water. Plus 5 grams of sodium hydroxide, because you need the total grams. Okay? Times 100%. And if I do that math, I will get 0.249%. Okay? If I wanted to calculate the mass percent of water, I could take 100%, subtract that. That would be the mass percent of sodium hydroxide, right? That's sodium hydroxide. So I'd take the mass percent of that, subtract it from 100. That would give me the mass percent of water. Or I could simply just take the water, move it up here, and so, replace 5 with 2,000 and do the same math, and I would get the same number. I'll let you do that one on your own. I think you get the idea. Okay, so let's deal with ppm. So we know we were given, let's see, so we know we have 5 grams of sodium hydroxide, and the total amount is 2,005 grams. 2,000 grams from the water. Whoops. Yeah. 2,000 grams from the water, 5 grams from the sodium hydroxide. So we have a total of 2,005 grams and 5 grams of sodium hydroxide. And so we can convert grams of sodium hydroxide into milligrams. So we got, in milligrams, that would be 5,000 milligrams. Okay? And we can convert this to 2.005 kilograms. So when there's a million milligrams, there's 1 million milligrams in 1 kilogram. Okay? So what I can then do is say that I got 5,000 milligrams sodium hydroxide, and I can divide that by 2.005 kilograms of total amount. And what I'm going to get, milligrams per kilogram, or if we're just, and so I got this, and so what I get is 2,494 milligrams per kilogram. And a milligram per kilogram, because there's 1 million milligrams in 1 kilogram, it's the same number, but it's also in ppm. So that's an example how to use this data that I just gave you and to calculate all of these different things. Now I want to go ahead and have you do some more math, but this time we're going to interconvert between these different things here. So if you know one thing, you can use it to calculate the others and vice versa. So we'll do a few examples like that because I think that's pretty helpful to be able to do that. So let's do that. So let's start off, I would say, easy. It's all relative, right? So let's say I give you, let's say we have, let me think. I have a 3.00% solution by mass. So this is a mass percent. Just make sure you get that. It's mass percent. Solution of sodium chloride in water. Okay? I want you to use just that information to give me what is the mole fraction of sodium chloride and what is the molality of sodium chloride. So we'll try to break this down, and I'll show you how to think about this to solve it. There's kind of a trick to this which makes it, at first it makes people feel uneasy when they try this trick, but as you use it, you'll realize that it actually can make some sense. So the way to think about this, and this is the part that usually gets people messed up, is you have to assume a certain number of grams of solution. Now remember, a gram of solution would be grams of solute plus the grams of solvent. And together, when you add those together, you get grams of solution. Well, this is a key thing you have to understand. If I had something that was 3% sodium chloride, so I had a 3% solution of sodium chloride in water, that means that 3% of the sodium chloride is representing the total amount of sodium chloride plus the water. So, in other words, so 3 grams of sodium chloride, if I use, let's say I assume 100 grams of solution, so let's try that. Let's assume 100 grams of solution. And 100 is pretty handy because percent means per 100. And that per 100 then can be a nice amount of solution to assume. Now, this is the part that makes people feel uncomfortable because they somehow think, especially if you haven't done this before, that if you assumed a different amount that you'd get different answers, but you won't. You see, a 3% solution is 3%, whether we're talking about 100 grams of solution or 1,000 grams of solution or 5,000 grams of solution. It's still 3% of that solution is sodium chloride. So pick something easy. So if we assume that we have 3 grams of solution, then we know that, 100 grams of solution, then we know that 3 grams is sodium chloride. And if we subtract the sodium chloride from 100, then we know that 97 grams is water. We know everything now that we need to know in order to calculate these two things. You see, we can convert this to moles to get mole fraction, and we can convert the moles, we still need moles of sodium chloride, but then we can convert that to 97 grams to kilograms in order to get the molality. So let's first calculate moles. You know how to do that, so we'll do it. We know that sodium chloride is 58.44 grams per mole, and water is 18.016. You can round if you want. I'll just keep it that way. So those are my molar masses, so I can now calculate my moles. For moles of sodium chloride, I get 0.0513 moles. And I think it's useful to make sure your labels include not only that it's moles, but moles of what? Moles of sodium hydroxide. You see, when you start doing this stuff, you got to keep track of what the substance is in order to keep up with it. And then we can calculate the moles of water and double check my math. Make sure I didn't do any fat finger mistakes when I was adding these things in. All right, now we got our basic stuff we need to get her done. Okay, so I'm going to shrink this down a little bit so I can make some more room. So when I get the sodium chloride, I want mole fraction, so I take my 0.0513 moles of, I just realized this, I wrote sodium hydroxide, that's sodium chloride. Okay, we just did sodium hydroxide on the other thing, and that's transferred over by mistake. And then we simply take the 513 moles sodium chloride plus the 5.38 moles H2O, and we can do the math, and I get 0.00945 mole fraction, and again, there's no units. See, the moles all cancel out. And so we got that, so that's our mole fraction of sodium chloride. You can double check my math. Pretty sure that's right, though. Then the other thing is molal. And that's pretty easy because I already know my moles of sodium chloride. And I divide that by 0.09700 kilograms of water. And I'll get my molality then. And that gives me 0.529 molal, or moles of sodium chloride divided by kilograms of water. And so that's one example. I want to give you one more that we can work through. Okay, I'm going to give you some statistics here. So we're going to deal with sucrose. Sucrose, you may know as table sugar. Okay, and table sugar, sucrose, has a molar mass of sucrose. Well, I'm going to try something. Let's see how it works. Hey Siri, what is the molar mass of sucrose?
The answer I found is 342.116 atomic mass units.
Okay, thank you. 342.116 grams per mole. Okay, so that's useful. And I know that a 15% by mass solution of sucrose, aqueous. You know, if I say an aqueous solution, that means that the solvent is water. Whenever you see the word aqueous, or what I just wrote there, if I put AQ in parentheses, that is being dissolved in water. So it's 15% sucrose by water, and that solution has a density of, let's see, what is the density? 1.059. And that's grams per milliliter. And so I'm going to be real specific here. That's grams of solution, because it's the density of the solution, divided by milliliters of solution. Okay? So that's what density is, 1.059 grams of solution per milliliters of solution. That's how you express density. And I want you to think about that. That's density of the solution. So that's total grams of solution divided by total milliliters of solution. And a 15% sucrose solution by weight has this density, 1.059. So here's what I want you to be able to calculate. What is the molarity? Moles per liter. What is it? So we can calculate that with this information. We can cross-calculate, okay? And to do this, we do one of these same kind of things. We can make an assumption. Now, since we want to remember what molarity is, and I think it's useful to actually write it out. It's, in this case, we want moles of sucrose per liter of solution. Notice this is mils of solution, but here we want liters of solution. So how do you think we could make that work real easy? Because you probably understand that the density of a solution, if you have a 1.059 gram per milliliter density, that would be the same density whether you had 100 milliliters, 1,000 milliliters, 1 million milliliters. It wouldn't make a difference because it all have the same density. Doesn't matter what the volume is. The density is always going to be the same. So we can assume again. So since we want liters of solution on the bottom, let's just assume that we had 1 liter of solution. So I'm going to assume 1 liter of solution. And if I assume 1 liter of solution, well, here's what happens. Then I can multiply the density times 1 liter, or 1,000 milliliters of solution. Okay? And the milliliters of solution cancel out. And what am I left with? Grams of solution. So I know that 1 liter of this solution has 1,059 grams of solution. So I'm assuming 1 liter of solution. I forgot to write the liter there. And that means in that 1 liter of solution, I have 1,059 grams of solution. Here's where we can use the percent now. I know that 15% of this 1,059 grams of solution is sucrose because it's 15%. So if I want to know grams of sucrose, if I assume 1 liter of solution, then I can figure out how many grams of sucrose are there by simply taking 0.15, that's the same as 15%, right? That's my percent by weight times the 1,059 grams of sucrose. And if I do that, I get 158.9 grams of sucrose. And then if I subtract that from the 1,059, I know that I'll have grams of water then too. So I'll know my grams. I don't need grams of water for this part. That's only if I was doing some more things. Well, yeah, I'll just leave it at this. So I have that many grams of sucrose in 1 liter of solution. I'm assuming 1 liter of solution. That's why I'm putting that there. And I know if I assume 1 liter of solution, that gives me a total number of grams of solution of 1,059. And by applying the percent mass, I know that I had 158.9 grams of sucrose per liter of solution. And I'm really close now to getting me where I need to go. I want to convert this 159 grams of sucrose per liter to moles per liter. So I need to use the molar mass that we just looked up. 342.116. So I can go ahead now. Take my 158.9 grams, divide by 342.116 grams per mole. Grams cancel out, moles flips up on top, per liter of solution. And now if I do all this math, I can tell you what the molarity is. 0.464 molar, or moles per liter of solution. So you see how you do this? You make an assumption in this case, and I just make a convenient assumption. The truth is, you can make any assumption you want. Any amount of will work. I just happen to, I like using, not sure, I think that's how that goes. I like using the 1,000 milliliters when I'm trying to convert to molarity, because molarity, I want 1 liter of solution. And in the other case, when I'm just dealing with only 1% and I have to convert that to, well, molality like I did before, then I assume 100. I just assume a number that's convenient, but you could assume any number as long as you do all the right math. Everything will work out to the same answers I got. If you don't believe me, try it. So that's this part. So it takes a little time, takes a lot of practice. So this section here doesn't really, well, it doesn't, I'm just kind of jumping into gases here a little bit, because we will use molarity in a minute. So because of that, I am okay with using that. So here's where we'll use molarity. But just want to take a moment talking about gases. Funny thing about gases is the relationship between temperature and solubility is different than it is if you want to look at solubility of a gas in a liquid versus solubility of a solid in a liquid. Usually, for most solids, if you increase the temperature, you'll increase the solubility of that solid. So if I want to get more sodium chloride into solution, I could heat it up and I could get more sodium chloride into solution. Gases is just the opposite. And the way I look at it is this. If I have O2, I'll just draw O2 molecule, okay? I'm not going to put the electrons. So if I have O2 here, it's going to be held in place by induced dipole-dipole moment, right? So it's going to interact with water. So this is going to induce a dipole where this will have a partial positive charge and this will have a partial negative charge. So when you put the oxygen from the water nearby, it's going to push the electrons to one side of the molecule, inducing a dipole. Okay? So then the H's from the water on this side are going to interact. If the oxygen is not held in place by its interactions with the water, since it's a gas, it will just float back off out of the water. So it will disappear. And unlike a solid, which will, it's all going to be in that solution. So if I were to draw a solution with a solid, okay, my solid's right here. And if I have some solid particles dissolved by the water and they become undissolved, they just fall right back. Okay, and that's where we get our dynamic equilibrium from that we talked about earlier in the other video. Well, anyway, something else is happening here. Because the O2 is a gas, when it's not being held by the water, it floats away. And so if you increase the heat, see, the heat part is what helps break apart the interactions of the solid if we're dealing with solids. So the reason why increasing the temperature helps to get things into solution is that because it helps the solid to break apart and reform new interactions with the water or the liquid. In the case of a gas, that's not needed. Temperature will only disrupt the interaction that takes place between the gas and the liquid. Increasing the temperature increases the kinetic energy, which allows this oxygen to float off. Okay? Now here's something I referred to before, and it's actually, if you're a Fisher person, you might appreciate this. think about the induced dipole interactions that oxygen has with water. Remember, this can't hydrogen bond because this oxygen is not the right kind of oxygen. It's not connected in a polar covalent bond. This is nonpolar oxygen. They're both oxygens, so there's no net dipole. You can only induce one, and that's what's happening here. So imagine if you're a trout fisher, you would know that trout hang out in cold water. And the reason why that is because in cold water, there is more dissolved oxygen. The cold water, there's less kinetic energy to break apart the induced dipole interaction that's holding the oxygen in place. As you increase the warmth of the water, the solubility decreases. And so that's why you won't find trout living healthy in a warm water environment. Other fish, they have less oxygen need. They have better ways of managing their oxygen. Some fish will even breathe air, like alligator gar can breathe air as well as stay underwater, so it does both. And so alligator gar can live in very warm, low oxygen environments because it can get its oxygen through other means. But a trout just can't do that. And so a trout, the way its metabolism is, it needs a higher oxygen amount in the water, and so it's stuck. It's stuck doing this cold water stuff where the kinetic energy is not strong enough to overcome the interactions holding the oxygen in place so the fish can use it. So that's something that happens, and we can do that from time. We can anyway, you get the picture. So it's the opposite as what you would expect. So if you heat up the solvent, you're going to lose the solubility of that, whatever that gas is. So if you heat up the system, less solubility of a gas. Now the other thing that comes into place, and this is one of those funny things again that can help you explain something that you are very familiar with because you've experienced it before in your life, I guarantee it, and that is gas's solubility is directly proportional to whatever the partial pressure of that gas is above that liquid. If I increase the partial pressure of that gas above the liquid, the solubility of that gas also increases. So if we look at this example, if we have a low partial pressure of a gas, there'll be a lower concentration of that gas here. But if we have a higher partial pressure here, there'll be a higher concentration. And it kind of makes sense because if there's a higher pressure here, that means there's more molecules interacting with this solution, and it kind of pushes it into solution if there's more molecules. And if there's less, there's not as much of a push to get into solution. This relationship is known as Henry's law, and it can be stated as the concentration of a gas, I'll make this a little bigger here, the concentration of a gas in a liquid is directly proportional to the partial pressure of that gas above the liquid. And the proportionality constant relates the two, and that proportionality constant is different for every gas and every solvent, and that's something you would have to look up. It's called the Henry's law constant. So whenever you take for a given solvent and solute, that solute being a gas, the concentration divided by the partial pressure is always going to get a constant. So what that means is if you know the relationship between one partial pressure and the concentration that results, that's going to be equal to a different partial pressure and concentration pair. So if you know any three of these, you can calculate the one that's missing. And so you can do a math problem like that. So let's go there. But before I do the math problem, I wanted to tell you something that you've all seen before. How many of you ever done this? You open up a can of soda. So we got our can of soda here. Okay. I'll just say Coke, and you open the top up and it goes shooting out. Well, that's Henry's law at work. You see, when the cap is closed, there's a fixed, the pressure of CO2 is high. Therefore, CO2 concentration in the liquid is high. Okay. When you open this, partial pressure of CO2 decreases rapidly. And so does the solubility of that gas. So the concentration of that gas also decreases rapidly. And when it happens rapid enough, all the CO2 just starts squirting out of the can, and it pushes a lot of liquid with it. So you've all experienced Henry's law. And so I'd like you to be able to explain that relationship. It also is connected to the bends, which is something that can happen with scuba diving. When people go down below at low pressures, when they're at really low pressures, high pressures as they dive deeper, the concentration of the gas that's dissolved in the blood increases. And so if you were to suddenly come up from that depth, you would get a similar situation that you see like with this Coke. The gas would suddenly come out of your blood and you'd get air bubbles because the solubility changes as the pressure changes. So that's why people, when they do go scuba diving or something along those lines, they have to ease up out of the depths so that the change in the solubility can be handled by the body without generating air bubbles, which can be deadly. And so the bends can be very serious. So you got, I'd probably gather most of us haven't scuba dived and had to worry about the bends, but I would say definitely we had to worry about how we opened up a can of soda or beer or whatever and have it squirt all over the place. That's because we had a rapid change in pressure above the liquid, and that rapidly changed the concentration of the gas in the solubility of that gas in the liquid, and it just came squirting out all over the place. So let's do a Henry's law calculation. So here it is. It says a sample contains oxygen at 20 degrees, so we have a 20-degree sample, with PO2 at 0.21 atmospheres above the solution. A solubility of O2 is 1.38 times 10 to the third molar. The partial pressure of O2 is then increased to 0.27 from 0.21. What is the solubility of that oxygen going to be? Well, that's just a matter of setting up the ratio again. So we know that the concentration of our gas is 1.38 times 10 to the minus third molar, and we know that's what it is when you have 0.21 atmospheres. Okay? And so we go ahead and set that equal to, well, we want to know what the new concentration is, because we don't know that, but we want to know what is the concentration now at 0.27 atmospheres. So we can do the math, which I assume you can do, and when I punch that in, I get 1.77 times 10 to the minus third molar. I would expect it to be higher when my partial pressure is higher, and I certainly have seen that. So hopefully you get a number like that. So that's the end of this part of this section.
Alright, real simple prank. Step 1, grab a can of pop, start shaking it. After shaking the can for, 5-10 minutes, we're going to put it on this vibrating chair back massager. Just let it sit for a little bit, let it vibrate. Who knows what it'll do, but it can't hurt. Alright, my next step here is I'm going to boil some water. Obviously, when you do this step, you want to make sure it's right around the time you're going to execute the prank. So, my buddy usually comes home about 6:30. It's about 6:15 right now. So the timing should be alright. It's pretty warm right now. What you want to make sure also is that it's not hot. So when he touches the can, he's going to know something's up. So make sure you give enough time to let it cool. Alright, he's coming right now, so just make sure I'm going to pretend I'm doing stuff, whatever. Hey, it sounds so stupid, but I busted my finger. Can you open this can for me? Yeah, I guess. Are you serious? Dude, that's not